Now that we have the tools we need to solve exponential equations, let's apply that for some word problems. Here's a population problem where we are told that we have a country, Fredonia, whose initial population is 200,000, and it's growing at a rate of 3% each year. So it turns out that with that description, we can model the population with an exponential function. 200,000 times 1.03 raised to the t, where t is the number of years that elapse. So for example, to figure out what the population will be in 10 years, we just plug a 10 in for t. So what we would like to do is figure out when will the population reach a certain size. According to this formula, when will we have a population of 300,000? In order to answer that, what we need to do is take the population function we have, set it equal to 300,000, and solve for t. So starting with this equation, our first step will be to divide both sides by the coefficient 200,000. On the right side, we see 300,000 divided by 200,000, which can be simplified to 1.5. So now we really have the equation 1.03 raised to the t equals 1.5. To get that exponent out front, we'll take a logarithm of both sides first, and then apply the rule of exponents. So now I have t times a number, and I can isolate t if I divide both sides by that number. So this is an exact value, and if I evaluate this quantity on my calculator, I get approximately 13.7. And in the context of this word problem, we should have a word answer, so we'll interpret this t value as a number of years, and say that the population will reach 300,000 in approximately 13.7 years. Here's another example. This one's from economics. Imagine that you have money that you set aside, you don't spend it now. Later on, you're going to buy something with it, but it turns out that what we generally see is a certain amount of money can buy less and less each year that passes. For example, my father told me when he was a kid he could buy a hamburger from a fast food restaurant for 25 cents. You can't really do that anymore. 25 cents doesn't buy as much as it used to. This phenomenon is known as inflation, the fact that the purchasing power of a dollar decreases over time. Or in this example, the purchasing power of $5,000 will decrease over time. And assume we're given a formula for the purchasing power of $a. Perhaps this is in an economics class. And you want to figure out how long it will take for the $5,000 you started with to only be able to buy as much as $4,000 would be able to buy today. So what you're going to do is take that initial $5,000 and plug it in as A, and then ask when will that quantity be equal to 4,000. And this is an exponential equation just like those we've been solving already. So we'll start out by dividing both sides by 5,000. And then because we see base e, it's a good idea to use a natural logarithm here. Take the natural logarithm of both sides, use a property of logarithms to bring the exponent negative 0.03t out front. And then remember that natural log of e is equal to 1. So the left side is just negative 0.03t. Now I'm going to move that over by dividing both sides by the coefficient that isolates t. Now you might look at this and be worried that you're going to end up with a negative number because you're dividing by a negative number here. But it turns out that natural log of 0.8 is also negative. So a negative divided by a negative will give us a positive. And that's exactly what we get. So it turns out if you have $5,000 right now and wait this many years to spend it, according to this model, the amount you'll be able to buy in 7.4 years with $5,000 is equivalent to what you could buy now with just $4,000. So in about 7.4 years, $5,000 will only be able to buy as much as $4,000 can buy today, according to this particular model.